Hello, everyone. So now we're going to talk about our hardware-in-the-loop testing solution for the latest traveling wave fault locators. So traveling waves are the voltage and current waves which propagates along the line because of the transient behavior of the inductance and capacitance present in the line. Traveling waves are always present during events such as line energization, switching operations, lightning strikes, and also during faults. For example, on overhead lines, traveling wave, it has a propagation speed close to speed of light. So that is almost 300 meters during 1 microsecond, which is very fast transient and is also very hard to capture. Other than the propagation speed, the characteristic impedance is also an important parameter we consider when it comes to the study of the reflection and transmission of traveling waves. On the right, these are some current waveforms from a simulation of a single line to ground fault on phase A. If we zoom in the phase A current, we could see these step changes. These step changes will propagate to both ends of the line in the terms of current traveling waves. If we apply certain filters to these waveforms, we will be able to capture the traveling wave peaks. So the arrival time and polarity of these traveling wave peaks are critical information since they indicate the direction of the traveling wave as well as the fault location. As I mentioned, when the fault occurs, if it is not at a zero inception angle, it will launch traveling waves. And these traveling waves will be reflected at the bus terminals and also at any discontinuities of characteristic impedance. So the Billy diagram on the right, it shows how the traveling waves are reflected at the bus and also at the fault location. In reality, it will be more complicated than this since you also have the reflection from behind the bus, and you could have a hybrid line which has both overhead lines and underground cables, or you could also have multi-terminal lines. The traveling wave-based protective relays, such as the Schweizer T400L, they have two different fault locating algorithms based on traveling waves. The first one is double-ended fault locating algorithm, and the other one is single-ended. In the double-ended traveling wave fault locating algorithm, the relay uses the information from both ends of the line. So this would require a communication media between the two substations. In this case, the relay would detect the arrival time of the traveling wave from the fault location and exchange this information with the other relay. So based on time difference between the two arrival times, the relay will be able to calculate the fault location. In single-ended traveling wave fault locating algorithm, it uses only the local measurement. So in this case, there is no communication channel which is required. So among all the traveling waves the relay detects, it will determine which one is the initial traveling wave and which one is the first reflection from the fault location. This is more challenging since you could also have the reflection from behind the bus and also from the other end of the line, which may arrive earlier than the first reflection from the fault location. So this depends on where the fault is. At the same time, to test the single-ended traveling wave fault locating algorithm is also more challenging. We need to provide very accurate and precise models to perform the test. In terms of the testing requirements, if you would like to test the performance or to validate the settings of a traveling wave-based protective relay with your own power system models, we need to have the capability to simulate power system at a very small time steps. So here we're talking about hundreds of nanoseconds. And also the signals that we inject to the relay will need to have a very high sampling rate, higher than 1 megahertz. In this way, the relay will be properly capture the traveling wave peaks. And most importantly, we need to have precise line models to produce the transients of traveling wave. When it comes to commissioning tests in the field, the current solution on the market is to superimpose the traveling wave peaks together with the fundamental frequency signals. So in this case, the timing and the polarity of the traveling wave peaks injection is very important. In our today's demo, we are testing the double-ended fault locating algorithm, as well as the traveling wave 87, which is the differential protection scheme, and we're using two Schweizer T400L relays. On the simulator, we're simulating a double-in-feed transmission line model. We're using three-phase distributed parameter line, which is 100 kilometers. The model is running on FPGA at a time step of 500 nanoseconds. From the simulation, the voltage and current measurements are taken from the FPGA, and it's sent out from the simulator through the analog channels to the relay under test. And this is done through the low voltage test interface on the relay. On the relay side, there is a point-to-point fiber optic link, which is used to exchange information for the differential protection channel. So now I will go to RTLab, which is our user interface of the simulation environment. So right here, users could create projects with different models and could assign a certain model to a target to start a simulation. And you could also have the control of the simulation. You can load the model, execute the model, and recite the model. So now we're going to take a look at the model we're running today. So here is the model shown in MATLAB Simulink. And in the model, we have two main subsystems. The first one is SC console, which works as a user interface during the real-time simulation. So here we have some scopes which are used to display the signals from the simulation for monitoring purpose. And also on the right, we have some control components which can send command to the simulation. So these ones will work as inputs to FPGA. Here we have three control blocks, which is to apply the fault on different phases. And also we have a block which can map the simulation signals from FPGA to different analog channels, which is connected to the relay under test. The other subsystem we have is the master computation subsystem, which will be executed in real time on the simulator. So here we take the inputs from the console, and then the signals will be sent to a EHS block. EHS, it stands for Electrical Hardware Software, which is the software that we use to map power system components to FPGA. So by using EHS, we let the users to stay at a circuit editor level, so we avoid any programming of the FPGA or the compilation of bit stream. So here, if I click on the EHS block, we have the interface. We have the interface to select which power network we would like to simulate, and we could also specify the time step, which is 500 nanoseconds here. So if I click on Edit, this is the model I talked about earlier. So we have two voltage source on both ends, and then we have a small segments of DPL after the source. And here, the two segments of DPLs are the line model that we are trying to protecting today. The first segment is 30 kilometers, and the other one is 70 kilometers. So please remember this number. When we're testing the relay, we need to check whether the fault location detected by the relay actually match the 30 kilometers. And here we have the fault breakers, which we control from the console. And in the model, we also have the current measurement and the voltage measurements. These measurements will be sent out as analog signals to the relay under test. So now let's move back to RTLab. I already loaded the model, so since we don't have a web camera today, I will just show you from the HMI of the relay. So since the simulation is not running right now, we don't have any voltage and current signals, and the relay is not armed yet. So now I'm going to start a simulation. And as you can see, the relay is armed, and also we see the current and voltage measurements. At the same time, when the simulation is running, we have the console on the right, which we could apply any modification to the real-time simulation. So right now, I'm going to apply a fault on phase A, for example. And as you can see, the relay has tripped, and it detects the fault is on phase A and ground. And the time domain distance protection element, the time domain directional element, as well as the traveling wave differential element has detected the fault. So to check the fault location, we're going to the event history, and we're going to download the waveforms from the relay. It has both 10 kilohertz record and the 1 megahertz record. So today we're going to just download the 10 kilohertz to save some time. And this report would contain the information of the waveforms as well as the fault location. So we'll just open the data file. And as you could see, the fault location is 229,987 kilometers. And these are the trip signals, the current signal, and voltage signals. We could also add the traveling wave differential element and also the time domain distance element. As you can see, the traveling wave elements will pick up the fault faster than the distance protection element. So right now, if you like to change the fault locations inside the model, what we can do is we can change this this model here. We can change the line length of each segment to vary the fault location. Instead of doing this manually, we could also have a script to automate this process. We have a small script here, and also this script here can be called from the Python API we have for the software. So it could be an automated test sequence where you start the model and then do the test, reset the model, and then change the fault location by calling the command in MATLAB. So in this case, you could run multiple test cases in one click. So that's my demo today. Thank you.